Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be talking about mass defect and nuclear binding energy. So let's get into this. So first I want to set a little context. So above me you can see a nuclear equation, and this is a typical nuclear equation that might happen in a nuclear power plant. So I'm going to use this as a springboard into talking about mass defect and nuclear binding energy. So what you'll notice here is I have kind of a table. And so for each of the reactants, I have listed their masses. So uranium-235 has this mass, and the neutron, this is a neutron, and that's the mass of the neutron. So just to go back to the equation, what I have here is the neutron bombardment of a uranium-235, and when that happens, that destabilizes the nucleus of the uranium, and as it decays into barium 140, krypton 93, and releases three more neutrons. And if this is in a nuclear reaction or a power plant, nuclear power plant, those three neutrons would be spread out to hit other uranium-235 atoms, continuing the chain reaction in the nuclear power plant. So here are the masses of the reactants, and here are the masses of the product. So barium 140 has this mass, krypton 93 has this mass, and then the three neutrons have this mass here. And if I add up the masses of the reactants, I get the total of 236.05258 AMUs. And then when I add up the masses of the products, I get 235.86769 AMUs. Now, you'll notice here that the masses of the reactants, the total mass of the reactants and the total mass of the products are not equal. And this might throw you off a little bit because we've learned that supposedly mass is neither created nor destroyed. That's the law of conservation of mass, right? So in normal everyday chemical reactions, mass is conserved, right? That's what we've been told. And here we see that mass is not conserved. So what is going on here? Well, this is special with regard to nuclear reactions. Mass is not conserved in nuclear reactions. So what we can do, and let me specify that this is referred to as the mass defect. There's a defect, there's something missing, there's mass that's missing in the process. So we can find the mass defect by subtracting the mass of the reactants from the mass of the products, or the mass of the products from the mass of the reactants, and we get this missing mass in AMUs, right? So we get 0.18489 AMUs of mass is missing in this process. Well, we can then convert the AMUs into kilograms. So we convert AMUs, this many AMUs, using the conversion factor that 1 AMU is equal to 1.66054 times 10 to the negative 7 kilograms. And then we get this many kilograms of mass. So 3.0702.10 to the times 10 to the 28 kilograms was lost during this nuclear reaction. So where did the energy go? That's the question, right? That's the main question. Like, so if mass is lost, where did it go? And that is where Einstein's equation E equals mc squared comes in, and I'll get to that right now. Just hold on tight. Okay, so now that I have the mass, the missing mass in terms of kilograms, right? So we looked at the mass of the reactants, looked at the mass of the products. We found that there's a difference, and we found that the difference between those masses, and that's the missing mass during this particular this nuclear reaction. And so now that we converted that missing mass from AMUs into kilograms, we can now use Einstein's equation E equals mc squared to find energy, right? So the great thing about this equation is that it relates mass to energy using the speed of light. So m is for mass, In this case, we're using the missing mass, the difference in the mass between reactants and products. So that's 3.0702 times 10 to the negative 28 kilograms. And then the speed of light, c, that's going to be, we're going to use 2.9979 times 10 to the 8 meters per second. And we plug that into Einstein's equation, and we get 2.7593 times 10 to the negative 11 joules of energy. So this is the amount of energy that is released when you combine those two things, or at least when you split the atom from uranium-235 to the other two atoms, barium and krypton. So that fission produces energy, and that energy came from the missing mass. So mass was converted into energy. How much energy? This amount of energy. So this amount of joules per one atom. Now, normally when we talk about energy, we're doing energy per mole. So let's convert this to moles. So if I convert, if this here is 2.7593 times 10 to the negative 11 joules per atom of uranium-235, I use the conversion factor. 1 mole is equal to 6.0221 times 10 to the 23rd uranium-235 atoms, and I get 1.6617 times 10 to the 13 joules per mole of uranium-235. So basically, this is 17 billion kilojoules of energy released per mole of uranium-235 that undergoes fission. To put this in perspective, a highly exothermic chemical reaction is about 1,000 kilojoules. Here we are producing 17 billion kilojoules per mole. So compare that with 1,000 kilojoules per mole. A nuclear fission reaction produces 1,000,000 times more energy than a chemical reaction could. So this is really important to keep in mind. So that's a lot of energy. So how does this relate to nuclear binding energy? So how does the mass defect that we're talking about relate to nuclear binding energy? Let's define our terms. Well, I've been using the word mass defect, and it's time to really specify what is meant by mass defect. Mass defect is the difference in the mass between the atom and the sum of the masses of the separated components. So basically what that is, it's a little bit different than what I was talking about before. What you are doing is, we know that the atom is made up of protons and neutrons, the nucleus anyway, and electrons. For nuclear reactions, we ignore the electrons mainly because they're very, very small, and their masses are so small that it's negligible compared to the overall size and mass of the atom. So when we're talking about mass, we're talking about the nucleus, and the nucleus is made up of protons and neutrons, and we call those particles of the nucleus nucleons. So we have these nucleons, and the atom is made up of these nucleons. So as a whole, we can compare the atom as a whole, the nucleus, when all of the nucleons are together, the protons and neutrons are together, what is the mass of that whole? And then we can separate those nucleons, separate the protons and the neutrons, and measure them individually. What's the mass of each individual proton, each individual neutron? Sorry about that. And we can take those separate masses and add those together and compare the sum of the individual particles, the nucleons, the protons and neutrons, and compare that to the nucleus as a whole when they're put together. And what we find is that the total masses of the separated nucleons is more than the mass of the atom when those nucleons are put together in a nucleus. So it's as when you take them from their separated parts to their whole, the whole has less mass than the parts, and that is strange, right? We don't see that in everyday life. So if you take a bunch of bricks, right, that would be as if if I'm building a wall, and I take a bunch of bricks and I find the masses of each individual brick and I total that up and I calculate it on my calculator, add them all up together, I get, like, say, 1,000 kilograms, right? But then I stack them together in a wall, and then I take the wall and I put on a scale and I find that the scale is only 900 kilograms. So I lost 100 kilograms when I took the bricks and just stacked them into a wall. That makes no sense. Like, where did the mass go? That doesn't happen. But in nuclear reactions, it does happen. And so in atoms, it does happen. So that is what we mean by the mass defect. There's a missing mass when you take the parts of the nucleus or the atom and then you put them together. Somehow when you take the individual parts of the nucleons and their masses and you just put them together in a nucleus, mass is lost. So we're going to look into that. And nuclear binding energy. What does that mean, nuclear binding energy? Well, that is the amount of energy required to break apart the nucleus into its component nucleons, right? So we have this nucleus that has the protons and neutrons tied together, right? They're attracted to each other. They're together in a nucleus. And the question is, well, how much energy would it take to separate those nucleons from each other? That energy that it takes to separate them out is called the nuclear binding energy. The reason for that is because there's some energy, there's an amount of energy that's used to bind them together, right? To overcome that binding energy, you have to put in some energy to separate them. So what is that binding energy? And we'll talk about that in just a moment. But let's go over another example to show what I'm talking about. Okay, let's go over this example. So the purpose of this example is to kind of show how we can take a nuclear reaction and use a particular reaction to figure out what the mass defect is and therefore figure out what the nuclear binding energy is. And so in this particular reaction, we have two hydrogen atoms combining with two neutrons to form a helium atom. So basically, if you think about it, what is a hydrogen atom? A hydrogen atom is just a proton, right? So here we're taking two protons and we're taking here two neutrons and we're putting together to form a helium atom. So basically, a helium atom, as we know, is made up of two protons and two neutrons, right? So in effect, what we're doing is we're using a nuclear equation to take the individual parts, the individual nucleons, the individual components of our helium atom that are separated, and we're bringing it together to form a helium. So as I said before, this relates to the mass defect, because if we know what the masses of the separated parts are, like the two hydrogens and the two neutrons, and we compare that to the atom itself when it's combined, in this case the helium atom, and we find a difference, well, that difference is the mass defect. So let's look into that. So here we calculate the mass of the individual parts themselves. So a hydrogen, a proton, is 1.00783 AMUs, and we have two of them in our equation. And we have a neutron, and the mass of a neutron is 1.00866 AMUs. And so we have two of those, and we calculate that, and we get the total mass of these separated neutrons and protons is 4.03298 AMUs. This is the mass of the individual particles separated from each other. They haven't been put together in an atom or in a nucleus. So now if we look at the mass of a helium atom, what's the mass of the helium atom? We measure the mass of the helium atom and we get 4.00260 AMUs. Well, now we total these up and we compare the totals. So here's the total of the individual neutrons and protons added together. And here's the mass of the helium atom itself with the protons and neutrons put together. And you'll see that there is a difference. And that is the mass defect. So we can calculate the mass defect by subtracting the larger value from the smaller value, and we get this value here. So 0.03038 AMUs is the missing mass. Well, where did that mass go? All we did was take the individual components and put them together. Where did the mass go? Well, that goes into the nuclear binding energy. So we saw with Einstein's equation that the missing mass must have been converted into energy. Well, what is that energy used for? Well, that energy is used to hold the nucleus together. So when you take the individual components of the nucleus and you put them together, remember that nuclear strong force that's binding things together? Well, that is the binding energy. So when you put the nucleus together, put the components together into an atom, into a nucleus, well, some of the mass is converted to binding energy, and that's what's holding the nucleus together. So we like to, in chemistry, use joules and kilojoules, but nuclear physicists love to use the unit of electron volts or mega electron volts. So here we have the conversion factor of mega electron volts to joules. So 1 mega electron volt is equal to 1.602 times 10 to the negative 13 joules. And a very useful conversion factor for finding nuclear binding energy from your mass defect is this one right here. Since mass defect is normally found in AMUs, the unit is AMU, it'd be nice to have a direct relationship between AMU and mega electron volts. And here it is. So 1 AMU is equal to 931.5 mega electron volts. So we can use that to find the nuclear binding energy. So here's our AMU. So we take this is our mass defect in AMUs. And so we take that mass defect and we use this conversion factor to convert it into the energy. And so here we get 28.30 mega electron volts. So this is the amount of energy that the mass was converted to, and this is the energy that's holding the particles, the nucleons together. That's the binding energy. So this is the binding energy holding it together. Now, it's useful to, this is the binding energy per nucleus, but every nucleus has a different number of nucleons. So it would be very useful if we could find the binding energy per nucleon. If we could have the binding energy per nucleon, then we could then use that binding energy per nucleon to compare with other nuclei and look at stability of the nucleus. So in this particular atom, we have 4 nucleons. So we can find the binding energy per nucleon by taking the binding energy we found. So here we're having a binding energy per nucleon. So we could take the total binding energy we found in mega electron volts, divide that by the number of nucleons we have in our nucleus, and then we get a 7.075 mega electron volts per nucleon. So here, this is the number of electron volts or mega electron volts per nucleon, and we can compare that with other nuclei. So for example, I have written here that carbon-12, the binding energy per nucleon for carbon-12 is 7.680 mega electron volts per nucleon. So if we're comparing this with this, you can see that carbon-12 has a higher binding energy per nucleon compared to helium. And what does that tell us? It tells us that the carbon-12 atom has more binding energy, so the nucleons are being bound together more tightly than that of the helium atom. And that's telling us that the carbon-12 atom is therefore more stable and has less potential energy. So the binding energy per nucleon helps us to identify more or less stable atoms. And so this is important because now we can make a curve that can compare the binding energies per nucleon of different atoms and show us what atoms are more stable or the most stable. And I'll get into that in just a moment, and that'll be the last part of this video. So hold on tight. Okay, last but not least, let's talk about the nuclear binding energy curve. And so here behind me, right here, is the nuclear binding energy curve. It's a rough sketch of it. You don't really need the numbers here. Here you have on the on the y-axis the binding energy per nucleon in mega electron volts. I didn't put in the numbers because it's not really that important. You can look this up in your textbook or find it on the internet with the numbers. But the main thing here is I want to show you what's happening in the curve. And so one thing I forgot to write down is on the bottom is your mass. So this is the mass of the nucleus, the mass of the atom that we're looking at. And this is the binding energy per nucleon. And what you'll notice is that the binding energy per nucleon is low for your smaller atoms that have less nucleons. So smaller mass means you have less binding energy. But as you get into larger atoms, the binding energy increases dramatically until you get to about a mass number of 60, right? So around 60 is where you get the highest binding energy. And it's really important to remember that higher binding energy means more stability, right? So the higher binding energy per nucleon, the more stable the atom. So here we have the most stable nuclides or nucleuses or isotopes here in this range, about 60, a mass number of 60. But then less than that, the binding energy per nucleon decreases and the binding energy per nucleon decreases here. So atoms that get larger than around 60 are going to be less stable here, and they're going to be less stable over here. So within here, you got the most stable because they have the highest binding energy per nucleon. So the important thing to remember here is also, I have written here fusion and fission here. So fission, larger atoms here are going to undergo fission, and that's going to release energy. Why is that going to release energy to undergo fission? Well, here you have a lower binding energy. If you split larger atoms into smaller ones, you're moving the atom. So here we're going smaller. So if we take a larger atom with a larger mass and break that into smaller atoms with less mass, right, then we're moving them towards more binding energy. We're increasing the binding energy, and therefore we're increasing the stability, and we're lowering the potential energy. So when you lower the potential energy, that energy is released. And so this explains why when you undergo fission, energy is released. Here again, for fusion, you're taking smaller atoms and you're putting together into larger ones. And again, when you do that, you're moving them closer, you're moving the mass closer in this direction such that the binding energy per nucleon increases, and again, becomes more stable and lowers the potential energy. And again, lowering that potential energy releases energy. This is analogous to what happens in chemical reactions when you're breaking weaker bonds to form stronger bonds. The stronger bonds are more stable and lower potential energy. And so when you're going from weaker bonds to stronger bonds, energy is released and is exothermic. So this is why fission and fusion releases energy. When you combine smaller atoms into larger atoms, you're making them more stable, higher binding energy per nucleon, more stability, less potential energy means energy is released in the process. Again, fission, you're taking larger atoms and you're splitting them into smaller ones. Again, making the smaller ones allows the binding energy per nucleon to increase. That's going to make them more stable, lower potential energy, releasing energy. So that's the last part of the video. I hope you found this interesting and fascinating, and I hope you learned something. If you did, then please make sure you like my video, hit the like button there, smash that like button, share my videos, subscribe to my channel. Make sure that you hit that notification bell. When you do hit the notification bell, make sure you click all so you can be notified by all the videos I put out. And also put a comment down below in the comment section. Let me know what you think and ask me any questions. I would love to hear from you. Thanks for joining me and have a great day.